I've written out again the classical component reasoning. So these three quantities here are just observables. They're measurable physical quantities. This is the z component along the z-axis of the spin. This is the x component of the same spin, s, and this is the z dashed component of the spin, where z dashed lies at angle theta relative to z. Okay? Now that's classical reasoning. Did that in the previous session, in the second half of the previous session. Now we assume so the next step is to assume that the correspondence principle applies here. And so we take this classical reasoning and then modify it somewhat into quantum mechanical type reasoning. And what we do is these observables then become, we translate them into quantum mechanical operators. So effectively we just put a hat over them, which makes them an operator. So we would then substitute the quantum mechanical operator for S of z, the z component of S, and similarly the x component of S. Now we know these. We know those 2x2 matrices from earlier sessions, and I've written them out here again, just to remind you. So you'll have a 2x2 matrix here and here, multiplied by these terms, and the result will be a 2x2 matrix. So you'll have a corresponding matrix for this operator. And once we have that, once we have the operator for the z dashed measurement, then we can find the eigenfunctions, the eigenvalues, expectation values. We know a lot. So a lot of quantum mechanics boils down to finding the appropriate operator, so that you can plug it into an eigenequation and then hence solve for the allowed measurable values. In other words, the eigenvalues and the eigenfunctions, or in this context, eigenfunctions tend to be called eigenvectors because that's what they are. They're column vectors, sometimes row vectors if you're talking bras. Alright, so here's the 2x2 matrix, operator matrix for S of x hat, and corresponding for S of z hat. We've done those before, so just plug these two matrices in here and here, and you'll end up with this. That's pretty trivial. You could do it for homework if you like, or you can just see it from inspection. Alright, so now we've got the operator for the z dashed component of the spin, so S z dashed hat. So plug it here. Here are your eigenfunctions, or vectors, because they're obviously column vectors, right? Just a 2-row, 1-column matrix. So obviously an eigenvector. Now here written out is this, your S z dashed. So you're rewriting this as this 2x2 matrix. Okay. Now it's an eigenequation, so it'll be the eigenvalue times the eigenfunction, eigenvector. So we're measuring the component, up or down, and we'll prove, independently of theta, we'll prove that there are only two eigenvalues. It's either the component is up the z dashed axis or down. So this mu here is your eigenvalue, and it will only take two values. We'll prove. Now, well, I won't prove. I'm asking you to prove, because it's homework, right? So actually solve this equation. Well, there's two equations there. So, for example, well, forgetting about the h bar. So you'll have cos theta a plus sine theta b equals mu a, and you'll have sine theta a minus cos theta b equals mu b. So you have two equations. You can solve for mu, and you'll get two answers, only two, and they are again the same as with the z component case, but now you're doing it for the z dash component case at an angle theta relative to z. And again, you get the eigenvalues plus or minus h bar over 2. Right? Interesting. So you're getting the same eigenvalues, even though different orientations. You know, the z-axis here, let's say it's vertical. Let's say the z-axis is vertical, and the z-dashed axis is at some angle theta, say, to that z, vertical z-axis. But no matter what the angle theta is, because it's quite general, you get the eigenvalues the same. They're plus or minus h bar over 2. Alright, so we've solved for the eigenvalues. Now, again, for homework, solve for A and B. What are the eigenfunctions, the eigenvectors? What are the values A and B? Now that you know what these are, you can plug in plus h bar over 2, so these will cancel. So you will have cos theta A plus sine theta B equals A, because the h bar over 2 cancel because of this, and you'll have sine theta A minus cos theta B equals B. Well, you got two equations there, two unknowns, A and B. You can solve for those. You do it for homework, and you will get the following two eigenvectors, or eigenfunctions, eigenstates, many labels. Okay? And this is what you get. Now this is a little bit harder. You'll need some trigonometry from high school, involving sines and cosines and stuff like that. So to solve for A and B, and for the eigenvalue up, plus h bar over 2, the corresponding eigenvector, eigenfunction, it works out, by solving this equation for A and B, it works out to be cos theta over 2 sine theta over 2 as a column vector. Right? Now, this theta over 2 may not seem much, but I promised you in the first session I would talk about some weirdness. And the source of the weirdness, this quantum weirdness, in the context of spin component measurements, is this theta over 2. So I'm just giving you a hint of what's to come in the next session. But the source of it is this theta over 2. Alright? Now, for the other eigenvalue minus h bar over 2, the corresponding eigenvector, so down dashed, that was up dashed, the dashed refers to the state you get after the wave function collapses when you measure the component along the z-dashed axis. Right? So the dashed refers to the z-dashed here. Right? Now for the eigenfunction corresponding to minus h bar over 2, you can see it becomes minus sine theta over 2 cos theta over 2. So again this theta over 2 appears. Right? Now that's for general theta. So let's talk a few cases, choose particular values of theta and analyze a little bit. So say when theta is 0, well that means that this orientation and this orientation, z dashed and z, are the same. Right? The angle is 0. So if theta is 0, this becomes 1, that becomes 0. So you just get 1, 0, which is from an earlier session is correct. That's 1, 0 was the eigenvector for this, right? Just the up state when you're measuring along the z, not z dash, the z component. Well, actually in this case they're the same, so it doesn't matter, right? And the down dashed, since this angle is nothing, will be the same as down, the down state, which is just 0, 1. Right? So all that fits. Now, what happens if you rotate the z-axis by 90 degrees, a right angle? So you go from here to here. Well, then your z dashed axis now corresponds to the old x-axis. Right? So it says this is what that's saying. So if theta is pi over 2, 90 degrees, then this state, this eigenvector becomes, we'll just plug in theta as pi over 2 here, so you get cos of pi over 4, that's cos of 45 degrees, that's 1 over root 2. And sine of pi over 4 is also 1 over root 2. So you'll get 1 over root 2, 1, 1 here. Okay? And for the down state, so you plug in pi over 2 here and here, and you'll get 1 over root 2 minus 1, 1. Okay? You'll get this. Alright, now remember the bigger picture. What we're doing here is discussing emphasizing more on the quantum mechanics, the physical concepts rather than the math. And we can do that. We can sort of de-emphasize the mathematics because these 2 by 2 matrices are so simple that there's virtually no math involved. It allows us to spend more effort, mental effort, on the physics, the weird physics that comes out of it. And next session you'll see how weird it gets, especially due to this theta over 2 thing. Okay, so what I'm going to do now is imagine you're performing 2 measurements. So imagine now you measure first the spin component along the z-axis. So let's say the z-axis is vertical. Okay? And then you'll get either an up or down state resulting. You'll get an eigenvalue corresponds to up, plus h bar over 2 component, or a minus. Now let's say you block the down. So the particles coming through that measure a down eigenvalue, they get blocked. And so the upper ones, they keep going through. So the particles travel through. Now the z-axis in practice, it tends to be a magnetic field, say a strong magnetic field, and so you have the 2 poles of the magnets, north and south. And the particle goes through the magnetic field, and the spin on the particle will influence the way the particle moves. Does it deflect up or down? Well, if it deflects down, block it. Just absorb it, block it. And that leaves the upper one. And then you use that upper state, which would be this one. So the up state resulting from your first measurement.